Okay, and in fact, this is not over yet. We have a third way of showing that um, the rho is outside of the derivative. Um, so this is a uh, like a new way of it's not new, but it's just a derivation of the Navier-Stokes equation from scratch. And if you um, do that carefully without making mistakes, you won't even have to think about the question of whether rho is outside or inside. You Because we're not focusing on a body of fluid with fixed mass. We're just looking at a region, uh, a region that is fixed in space, um, and we look at the amount of fluids, the amount of momentum goes inside the equation and outside the equation. So that's a different uh, point of view, a different perspective. Then so yeah, here we instead of following a volume of fluid, or not a volume, like a certain mass of fluid moving around in the field, in the velocity field, we just focus on a region V. Here V is not V of t, it's just V. Okay, it's just a fixed uh, it's just a fixed volume in space, V. And in this case, we have what's inside this, the rate of change of the momentum inside this volume is just partial derivative with respect to t and rho u dv. Yeah, so that's so rho u is the momentum density, dv is a volume element, but we integrate over this volume v, which is fixed in space. So we don't have a motion with respect to space. Here the derivative is just with respect to time, because there's no chain rule when you do the partial derivative. Sorry, when you do the total derivative of u, there is a chain rule, but in this case there's no chain rule because um, there's no derivative with respect to x. The volume is just fixed in space, and this this is equal to, so because now the perspective is different, we're looking at a fixed volume in space. The rate of change of momentum inside this fixed volume in space is not only caused by the force acting on that fluid enclosed by this volume, but also includes the amount of fluid actually moving into or outside the volume, right? So this is the advection term, and um, that's actually one of the extra terms if you do that in the point of view of a fixed volume. Then in this case, there is a term in addition to all the force terms that causes changing momentum inside this volume. We also have a term that causes by the that is caused by the physical motion of the fluid, and that's um, integral, right? U, right, and rho u ds. Sorry. Right. So this is the flux of momentum flowing with the fluid um, into the into the volume, right? So because here rho u dot ds is just the flux of the mass, and you multiply by u, that's a flux of momentum, and you can see that, right? This is a like a dyadic product dotted with a vector, so you still have a vector inside this integral, okay, and plus whatever force, right? Forces, right? Then if you use divergence theorem and take everything out of the integral and cancel the dv's, what you will find is partial rho u partial t plus, sorry, there's no plus, equals to minus, so using the divergence theorem, we'll find that the divergence of whatever inside, so it's rho u, a direct product with u. Okay, and this we now expand out both sides, so we have rho partial u partial t plus u partial rho partial t, and that's equals to minus u, so this is basically a product rule, u dot so there's no dot, so you have to make the result a vector, because divergence of a tensor is a vector, and this is u directly multiply the divergence of rho u, so the result is a vector, and also minus, so take rho u out, so you treat rho u as one vector and u as the other vector, rho u divergence of u. Okay, and I was being careless. So this term is not what should appears here, and this term is wrong. You should have a term which looks like rho u dot grad u. And why is that? So yeah, because like in this video series, so it's, again, I'm not like teaching or like trying to say anything that I assume you don't understand, or like make it an educational video. I'm not doing that. It's just a sharing of thought, and so I'll just go through every detail, because when I study, I feel that the lectures just don't go over all the details I need, and I have to like fill in the gaps, and that takes a lot of time. So yeah, if so like watching this video can be really boring if you are like very smart, and and just knows everything. But yeah, I'll just go over all the details in case someone is watching and those details will be helpful to them. So this um, this this divergence of rho u, right? So the nth term of that would be in Einstein summation or the index notation. That would be partial j rho u j ui, and then you do a product rule. That would be you first take rho uj out, so it's rho uj partial j ui, and again plus u plus ui partial j rho u j, and this is u divergence of rho u, and this is rho j, right? So that's u dot grad u, right? Okay, and when we have that, we can rearrange that equation so that we have rho partial u partial t plus u dot grad u, right? That's exactly what we want, and you will see that the rho is left out of the bracket, and you will expect the other terms will cancel, and what you have is just partial rho partial t plus partial rho partial t plus divergence of rho u, which indeed cancels, right? Which indeed cancels because that's just 0, and that's just the continuity equation, and this one is du by dt, and the whole thing, and you bring rho here, you will see that this term is the left hand side of the fourth equation, and rho is outside the bracket. So now in 3 ways we've shown that this rho should be outside the derivative, not inside for the most general case, and I think like this should make everyone happy about this part of the Navier-Stokes equation.